Okay, let's go through a tutorial of a composite in the materials like PDF 1, or in other words, this set of notes, composite lecture notes part 1. Okay, so this question is mainly focused on 2015 question, test exam questions, and therefore the first one is that discuss the three main types of fibers used in polymeric. Polymeric means that it's a polymer material, and their selection for structural components. As for the rest of the part B and C, I'll just move it somewhere else. The thing you should take note is that it's talking about discussing the three main types of the fibers. So it's not name. If the question say name the three main type, then you just name. If it says discuss, then you have to discuss the everything of the fibers. Alright, and therefore the first one to discuss is the glass fiber. And you're gonna explain that it is a silica form, alright, which comes in sand. So silica itself is sand, alright, and what makes sand is actually a silicon with a air. Alright, silicon and air, most probably I would say is oxygen. Alright, silica and oxygen, if you mix together, it becomes sand. So what comprises of the sand or silica is your silicon and your oxygen. Alright, so in nature, alright, sand comes naturally, alright, instead of the silicon, and it melts at this certain temperature. So once you melt the silica, you can create a certain fibers that you want, and it's through a fiberization process, which over here you actually melt your sand, your silica, at 1720 degrees Celsius. Alright, so once you melt it, alright, it becomes a stream of liquid, and it will comes into this thing where it will roll. Alright, this thing will roll and somewhat ensure that what comes out of it is actually a fiber. Alright, so therefore this is just the fiberization. Alright, and these things are called the rotating wheels. So you can enhance its properties by mixing with oxides, aluminium oxides, alright, where it's written as Al2O3, calcium oxide, I think is this one, and magnesium oxide, etc. Alright, so different materials will give you different properties. Alright, and example, aluminium oxide, alright, is good electrical insulation. So this is used for combination with your silica to create e-glass. Alright, then we'll talk about it. And high mechanical strength, high compressive strength, hardness. Alright, magnesium oxide also can help you to increase high hardness, alright, better melting point and things like that. Alright, calcium oxide. Not much description on the calcium oxide. So yeah, at least you know two lah. Okay. And then the glass fibers, alright, it can be in the form of S glass, E glass. Alright, S glass is for temperature and strength and stiffness. So you mix I mean most probably the magnesium. If it's E glass, you can mix with aluminum oxide for electrical insulator properties. Okay, and you may wonder fiberization process. So this is the picture for the fiberization process. Alright, so these are the things that you can find on your slides also. Next one is a carbon fiber. Alright, carbon fiber is organic material. Alright, anything that is once a living thing. Alright, for example, if you were to cook your meat, alright, if you were to burn it, alright, if you were to so-called cook too much, alright, below of the meat you will have certain black color char, alright, or chao da. So therefore over here organic materials are being so-called processed. So once you burn it, it becomes like black color, like carbon like that, or like a charcoal. So these organic materials will go through certain surface treatment through temperature adjustment. Alright, so there is three processes that could process the organic material. So also this three lah. Alright, so and you can memorize all these things. Alright, these are the processes. Alright, so I think okay, you have to go through these processes first, then you'll go through surface treatment with also different temperatures. Okay, so I should have rewritten it properly. Previously I've written this, I just cancel it first. Okay, this should be the one. So the organic material are processed with using these three methods. Then after the surface temperature, I would say that the surface treatment. Alright, surface treatment, you can adjust the temperature for different strength and stiffness. So I could just add in as for surface treatment, alright, before this thing, then adjust treatment for different, temperature for different things. So these are the things, and the process is called successive stages of pan pyrolysis. Alright, pyrolysis means you break down a certain organic material, that's all. Okay, and you may also want to understand all this. Alright, different tensile strength. Alright, these are the different groupings lah for your modulus. Okay, and yeah, you can just memorize this, yeah, if it's needed to be. Okay, we have done glass fiber, carbon fiber. Now we talk about ceramic fiber or Kevlar fiber, or you can call it the synthetic fiber. I believe. Be careful that synthetic fibers is a very big term works, alright, because it can contain polyester, acrylic, nylon, etc., including Kevlar. So therefore, Kevlar or aramid is one of the better words to actually describe your fibers, aramid fibers. And these are the things that you could own self read it out. Aromatic, alright, just now as I say, there is a word called aromatic polyamide. So aromatic itself, there's a term, it's called the purpose of it is that it is unusually stable. Okay, and because of its stability, alright, it's very difficult to cause aromatic molecules to break apart. So therefore it's a very strong bond, alright, and to react with other substances. So therefore in this case, Kevlar will be strong, while it also can be able to prevent any chemical reactions with other stuff. So therefore it's a very good material for Kevlar aramid. Alright, and it is a very strong covalent bond in fiber direction, or you call it a benzene ring, I think. Therefore in this direction, alright, when you pull it in this direction, this bond over here, as you can see, is a very thick bow line. Alright, is a so-called covalent bond. However, over here, alright, in this transverse direction is a hydrogen bond, which is a very weak one. So comparatively, the hydrogen is weaker than the covalent, and this is why it's very much an anisotropic system. Okay, and therefore for aramid, strong covalent bond in fiber direction, weak hydrogen bond in transverse direction, and is anisotropic, meaning it can allow certain direction of loading only. Alright, as you can see, if you were to pull in this direction, alright, it will break. You will so-called resist the breakage. But over here, if you were to pull it, it will straight away break, or it's very weak in this direction. Okay, so therefore it's good for dynamic loading, meaning I believe is moving loads, alright, or fatigues, alright, materials that will constantly experiences fatigue or whatever loadings or moving all around. Alright, so it's a high strain anisotropic materials properties. So as you can see, for tensile strain and tensile stress, alright, most probably tensile strain itself, aramid can be more applicable. Alright, as you can see, comparatively, Kevlar is not as good as S glass or E glass, but at least to a certain extent is viable because of its chemical properties, or because it's not very good. It's not very easy to actually react with other materials, which I believe is the key thing, and it is pretty stiff and strong also. Alright, don't compress it, but at least if you were to pull it, aramid itself is pretty good. But you need to know that aramid is not good for compressive, or because of where it develops kin bands. Alright, so over here the kin is just like that. Alright, so if you were to create this type of, so at first it was like that. Alright, so if you were to compress it, it will become like that. Okay, and therefore this kin over here will actually easily break because you're applying force in the transverse direction. So Kevlar in the transverse direction is very weak, so over here it will straight away break into two pieces like that. You see, so therefore Kevlar is not good for compressive loading. Alright, please take note of that. And the different applications, you can say for maybe Kevlar 29 is for protective apparel and things like that. 100 for ropes and cables. Alright, most probably colored one, I think. There's one question is that why they will compare why use K29 or why use K100. K100 is allows color, alright, I believe, if I never remember wrongly. Alright, as for K29 is just for normal colors. Alright, no need to to think about colors. If you don't need to think about colors, K29 can be used. If you want something that is colorful but protective, then you can use K100 Kevlar. For the last one, tensile strength 1.4 GPa compared with carbon fiber, I don't know what the hell, but you can just I've searched for the Kevlar. Alright, the tensile strength over here it's 3.6 or 3. Alright, and over here is also 3 or 2.8 for the tensile strength. So therefore, I don't know where the 1.4 comes in. Alright, you can actually watch this part. I also don't understand what he's trying to say. So yeah, give me a while.
Is 1.4 gigapascal, right? This is much higher than the 1.1 for E-glass and type 1 carbon fiber.
So therefore, yeah, he explains 1.4. There is certain reference, I believe, but I don't know where the reference is. And over here, we often give tensile strength of 3, but he's giving 1.4, so I don't know what the hell is going on already. Okay, I've searched for the reading materials. Alright, page what? Good question. Page 12. Alright. Yeah, your aramid is 1.4. Alright, compared to type 1 and type 2. Alright, this is what he's trying to say, I think. So therefore, as you can see, there is inconsistency in the thing. So I think you can just follow his 1.4 GPa, since I believe this reading material is from the Glasgow side. So therefore, you should follow that one rather than the other ones. Alright. Nonetheless, you can also search for this thing, alright, for this video, and you can watch this full thing for question 1, I think. Okay. And I think this is only for this video, I'm only answering part 1a. Okay. So we have identified glass fiber, carbon fiber, and your aramid fibers or your Kevlar fiber. Okay. So you have to discuss all these things. Alright. And these are all the selection criteria. Alright, there is also the last part of the questions. Alright, so they ask you to discuss the 3 main type of fibers used in polymer or plastics composite material, and what are the selection criteria for these fibers. So you will have to compare the cost. Alright, loading direction, is it anesotropic or isotropic? Isotropic will be cheaper. Okay, and the weight. Alright, because heavier the weight, it is also because if you want your overall product to be light, alright, the weight has to be in considerations. And then thermal expansion will lead to shrinkage. Alright, so you have to ensure that the fiber and the matrix have their thermal expansion coefficient about the same. Alright, so that they expand in the same rate. For example, I should say the thermal expansion rate, alright, RATE, okay, or RATE. So what I mean is that this is the matrix over here, or there will be a fiber. So if the fiber expand faster than the matrix, alright, then if you were to go into after it expand, the matrix itself will actually curl all around, you see, because of its expansion, and then it will becomes real very flimsy or whatever. So as you can see, at first it was this straight line. So as it curl, there will be a certain transverse loading already, because it's starting to bend, and because of this bending, actually it will break the fibers and it will cause the material to spoil. So therefore, the expansion between the matrix and the fibers has to be a certain same rate, so that once the matrix expand, it allows the fibers to also expand in the same direction, instead of curling around. Alright, instead of curling around and actually break at this point or wherever. Okay, hopefully this is clear. And you have to consider all the mechanical properties. Alright, mechanical properties. Alright, and its adhesion characteristics, because you're gonna stick your fibers onto the matrix. Adhesion is very important. Alright, how well can the fiber stick onto the matrix? The better it is to stick onto the matrix, the stronger the bond it is. Alright, so it's very important, and therefore this is the selection criteria for your fibers. And this is the part 1a attempt, and you can, yeah. For the next video, we'll talk about the other two parts. Alright, the 1b and 1c. Alright, and yeah.